Hello everyone, my name is Mohammad Reza Kolani. I'm a PhD student at the Chair of Computing in Civil and Building Engineering at the Technical University of Munich, and I'm going to present our paper titled Robotized Tower Crane Simulation and High-Level Action Planning System in this presentation. Tower crane are the most important and effective transportation devices on construction site, and almost every large-scale construction project utilize at least one tower crane with rental costs ranging from few hundreds to couple of thousand euros per hour, and this shows the importance of these devices in construction site. As construction sites move toward automation, the need for robotic and autonomous crane systems become apparent. While there are a lot of research on construction and on tower cranes field, most of this study focus on trajectory optimization of the hook and control strategy, and only limited of this research explore the integration of robotic technology into this field. In this study, we developed a robotic tower crane model, including all the geometric and kinematic and dynamic of tower crane to ensure a realistic and functional simulation within our framework. Furthermore, we developed a modular framework for simulating tower crane operation in a physics-based simulation engine and algorithm to automated tower crane operations. We built our platform on ROS, which stands for Robot Operating System, and is an open source framework that provides tools, libraries, and communication standard to build a modular, scalable, and real-time robotic application. It allows different nodes to interact using different communication types and making it ideal for controlling complex systems like robots and, in our case, crane. When ROS paired with a physics-based simulation engine like Gazebo, Unity, or ISARC, it enables realistic testing of robotic operations in virtual environment. These simulators replicate physical behavior such as gravity, inertia, friction, and collision. And this provides a powerful and important tools which reduce cost of real-world experiment for testing different scenarios with the real robot, or in our case, testing different scenarios with real tower crane. So as a first step toward our goal, we began transitioning from a CAD model to a simulation representation. This process involves simplifying the original design of tower crane by removing non-functional components and high-resolution meshes that are unnecessary for simulation. We then export the relevant geometry in suitable format, STL and DAE. Following this, we generate all necessary configuration files required for simulation, including the URDF and SDF for robot description and semantic information, and additional files for visualization, collision, and control integration. Our framework is composed of several raster nodes, which can be grouped into four main functional categories. First, we have the crane description, which includes the URDF model, including mesh files, mass properties, and inertia, all accurately extracted and processed from the original CAD model. This URDF is then parsed and published with the ROS system along with the joint state and relevant transforms, making it available to access the crane kinematics and dynamic structure. Second, we implement the planning modules. This includes an inverse kinematic solver to compute joint configuration for both initial and target position, and a motion planner to generate collision free paths connecting those configurations. Third, we integrate a control node. This node ensures smooth motion of all crane joints by applying velocity and acceleration profile tailored to the crane specific kinematic constraints. And finally, we have the simulation engine and visualization layer, which combines physics-based simulation backend for realistic interaction with the environment and RVs for real-time visualization. Through an user-friendly GUI, after completing all the part, the user can set a target location for the hook, then generate a path for this movement and trajectory, and then execute this movement by pressing the execute command here. And as a next step, we introduce an action management node, which handle the complete lifting operation autonomously, and some of the other operations completely autonomous. And it requires only high-level input from the user, such as source area or target area or the name of component or the ID. or the label, and I will explain it in the following slides. We develop a pipeline that autonomously handles the entire motion execution process based on high-level target goal provided by the user, high-level information from the user. Once the goal is received, the action management node, AMN, initialize the necessary module and nodes and interact with the movie through its API. As a next step, the system performing validation check to ensure that the target location is in the working space of tower crane. If the position is outside of these bounds, an error message is printed in the terminal and the user can understand that this is outside of the boundary and cannot perform. However, if the target is valid, the node invoke the custom action server to compute a motion plan and generate a full trajectory. This trajectory is then passed to the controller for execution. Through the entire process, an emergency stop feature is available, and any point the user can cancel the operation, and then the system immediately stop the motion and return the canceled goal to the terminal. Otherwise, once the trajectory is successfully executed, a successful message is returned to the user. In the next step, the user can not only provide the information for a single movement of crane, but can also provide the information for entire operation, like pick up column ID at the initial location and place it at the target position. And this information includes object position, initial and target, object name, and action type. Because in our action management node, we have different type of actions like lowering, lifting, transporting, and etc. And during this time, this node provide a feedback to the user, and user can monitor the process and statement through the terminal and also through the physics engine and visualization part. For example, for transporting object, it has a pipelines that go after receiving this information. It goes to this pipeline, like lowering the hook, then with the smooth movement, be close to the component, attach the component to the hook, because we don't have a human in the loop to actually attach the component to the hook. We do it via the function. Then lift your hook and transport and lower the hook and place it in the target location. We validate our framework and action management node with two different scenarios, including different type of component, different initial location, as you can see here, different target position, and different type of component. Action management node receive a high-level information of different object with different initial position and also different target location from the user, and then iterate through this list from the beginning to the end and start picking up the first object, transport it and place it into the target area, then continue with the second object, as you can see in this video, and then place it in the target area, then go to the safe zone and continue with the last component until this list is complete and all of the components are placed in their target area. As a conclusion of this presentation, we develop a modular framework for robotized tower crane to simulate the full functionalities of TC operation. We develop a physics-based simulation platform for testing and validating tower cranes operation before testing it with a real crane that can save a lot of cost and time. We developed the action management node to automate several tower crane operations. In future, we have a plan to test our framework with lab scale tower crane inside our lab. And we actually have a plan to integrate sensors to provide the occupancy map for optimal collision free pass, and integrate advanced control strategy to eliminate load swings by generating appropriate counter movement. And I gratefully acknowledge funding from TUM Innovation Network Co-Construct and the DFG Research Unit, the information backbone of robotized construction. And thank you all for your listening.